All right, folks, we are back for another segment of some regression analysis using Excel. In the last segment, we built a bivariate regression model that was captured pretty vividly in the scatter plot diagram on the screen, where we modeled sales on the y-axis as a function of only the ad spend variable on the x. We started by building a correlation matrix and recognizing that with respect to our sales variable, which is the one we wanted to predict in this column here, that the largest magnitude of correlation was that with the ad spend variable. And that was kind of our starting point in terms of just building a bivariate model when we only have one X predictor variable on the right-hand side of the regression equation. By the way, if you're looking at this and you're wondering why the top off-diagonal entries are filled in and they weren't in the last segment, I filled them in manually, recalling that they must be symmetric. These values are the same. These values are the same, so on and so forth across the diagonals. Okay, so I just kind of mirrored them so it's easier to look down any particular row or column. And we also want to identify that there are some other variables that, while not as strongly correlated with sales as ad spending are still positively correlated. For example, the promo variable, positively correlated, as are social media impressions. And the price variable was the only one that was negatively correlated, but the correlation is so small that it is likely to be significant if we include that variable in our model. And that is something we'll be able to check. You might remember from a previous segment on measures of association, we had a little bit of an ad hoc rule for thinking about the statistical significance of a correlation value or of a sample correlation. And that relied on just was this ad hoc rule where we took the square root of the size of the data set and we compared it to the number 2. We took the ratio of those two things, so it was 2 over root n. And in the case of 365 observations, that threshold comes out to around a correlation of 10% would define a significance threshold. So if the magnitudes are bigger than that with this data set, we would have some sort of significant correlation, but it may not mean it is significant with respect to the effect we measure in our regression model. So we're still going to have to check. For example, promo's correlation is bigger than 10%. It's around 0.31. Impression is also slightly larger than the ad hoc value of 10%. And again, that was the square root. And that was 2 divided by the square root of n, square root of 365 observations in this case. So what we're going to think about doing is building a multivariate regression model. Now, a multivariate model we cannot capture with a 2-dimensional scatter plot, so we're going to not really use a scatter plot to visualize a multivariate model, but the way we're going to build it using Excel and the way we're going to interpret the diagnostics is going to be fairly similar. And I'm going to go ahead for the moment and start by considering a model where we've added in not only ad spending, but we've also added in impressions, another numeric variable on the quote-unquote right-hand side of our regression equation. So we will now have a model with 2 predictors. Okay, if you're wondering why didn't I add promo in, its correlation's a little bit higher than impressions. Promo is a categorical variable. I will come back to that one momentarily. But let's suppose for the moment I wanted to build a model where we use our ad spend budget for the day and our social media impressions to predict the level of sales. So let me go back to our data set, keeping in mind I'm not really touching anything on the left side of the screen. That is all the raw data here in yellow. I'm just copying columns to the right to help keep things organized here. Not necessary for you to do that, but I like to be organized. And I'm going to go ahead and relabel the ad spend variable. I was calling that X. Let's switch that to X1 since now we're going to have multiple X variables. The other variable we were interested in were impressions from column H. So let's paste that over here. And we will call that variable X2. And again, if you want to format your columns just to keep things readable, that is appropriate. And we're going to go ahead now and we will again invoke our Excel function. So we're going to click on the data tab and I'm going to click on that data analysis button in the top right in the analyze subcategory here. And again, if you don't see that, you will need to follow the instructions in the prior segment, right click that space, customize the ribbon, make sure you've added the appropriate add-in, and you should be good to go with that. But let's go ahead. We're going to click that button, and we will now invoke the regression tool. I'm going to hit OK, just like we did last time. And our Y variable is not going to change. The only thing that is going to change is the X input range, where we're now going to have two X variables in the X input range. Okay, and I'm going to label this. We'll call this model 2 to distinguish it from model 1, which just had the single variable, and that was ad spend. This is going to have two predictor variables, two regressors, right? Two independent X variables, and that is ad spending and impressions, both numeric variables. And we'll go ahead and take a look at the model output here. Let me just zoom in a little bit. And again, we will format things so everything fits nicely. And the so a few things we want to be able to do here: interpret the model diagnostics in and of themselves, and then do a little bit of comparison to the other model. Which model is better at fitting the data that we have? Okay. First thing we should take note of here, most important column is the coefficients column. This is the column I need to get my values, my estimated values for beta 0, the intercept, beta 1, and beta 2, the coefficients on X1 ad spend and X2 impressions. And something might surprise you that the impressions effect is actually negative, which means if impressions goes up by 1 unit, sales goes down by 0.111 approximately. And that is the way to interpret that coefficient. And that might be surprising. However, a quick look at both the T statistic, which is definitely smaller than 2 in absolute value, and the P value, which is definitely larger than a 5% significance threshold, are both indicative of this not being statistically significant. This is a statistically insignificant variable that we've added here. Okay, impressions is not statistically significant. The other way that you can tell this is if you look at the confidence interval, you'll notice even the confidence interval is slightly confused about the direction of the effect that impressions has, in that the effect could be as low as minus 0.555, or it could be as high as positive 0.333. So you notice the confidence interval says the effect could be negative in some range and positive in another, right? Between the lower and upper bounds, meaning that confidence interval includes 0. It includes 0, consistent with the two-tailed hypothesis test telling us that that value that the blue arrow is pointing to is not statistically different than 0. That being said, if we look at the coefficient on ad spending, you may recognize that that value, roughly 19, is not much different than the corresponding value when we looked at model 1. So let me switch back to the model 1 tab just for a moment. Again, model 2's ad spend effect says if ad spend goes up by 1 unit, sales goes up by about 19, right? 18.96. Model 1 made about the same prediction. Ad spending goes up by 1 unit. Sales is going to go up by around 18.85, right? So almost, again, a 19-point effect if ad spend goes up by 1 unit in terms of a 19-point effect positively on sales. So notice between models 1 and 2, the prediction of how ad spending affects sales is fairly robust. That hasn't really changed here. And we can also see, looking across the row for the ad spending coefficient, that the T statistic is very large, the p-value is extremely small, and the lower and upper values of the confidence interval are both positive. They're not arguing about the effect in terms of the sign. Okay, so what happened here, we added a statistically insignificant X variable, that is impressions. This is statistically insignificant. All that information is consistent with that. Okay, that being said, you may note that our R squared is a little bit higher than what it was in the previous model. Okay, the R squared is at 0.5389. And if we look at the R squared in the model where we only had a single variable, it was a little bit lower, 0.5386, right? For the case where we only had one x-axis variable. Okay. That being said, you might remember, oh, didn't we want to use the adjusted R squared to think about whether or not we had added too many variables? And you'll notice in model 1, the adjusted R squared is 0.5374. But in model 2, the adjusted R squared is 0.5364. It's gone down, consistent with this notion that adding that extra variable, adding that impressions variable, which was statistically insignificant, added too much of a cost, too much complexity, and didn't provide enough benefit in terms of added variability in explaining sales to our model here. Okay. In terms of the residual standard error, you'll notice model 2 is not dramatically different than model 1. We are roughly 5,000 units off on average in predicting sales at any given day. Okay, 4,945. Model 1 is just a little bit better in terms of that regard. So model 1 kind of wins out in two aspects here. The adjusted R squared is higher, and the residual standard error is a little bit lower. If I had to pick two, which one actually is a better representation of the data here, I may be a little bit more favorable to model 1, even though it's using less information to predict the sales variable. Now, notice model 2, even though we have a variable that is insignificant, impressions, the overall model as a whole is still statistically significant. The p-value on the f-test is very close to 0, definitely smaller than that 5% threshold if we're using the p-value approach here, meaning model 2 is a case of a model that is jointly significant but has individual features that are not. The individual feature that is not here is the social media impressions, but ad spending is still significant, and the intercept term is still significant. Note again that the ad spend value of the coefficient, as well as the intercept coefficient, they didn't change very much when we included the impressions variable. They were both robust to the inclusion of the impressions variable. And you might want to say, all right, well, maybe we should take the impressions variable out at this point. I may agree with that. Okay, but to keep things moving here, let's consider actually adding another variable, okay, and proceeding with the analysis. Okay, now, when we looked back at the correlation matrix earlier, we recognized that there were a few things that were positively correlated with sales. And what were those things? Well, we started with ad spend. We just looked at impressions, and we saw impressions was not statistically significant. And so maybe I'll just put a little X over that. So remember that was not significant. If impressions wasn't significant, I'm going to argue price is also not going to be significant, but make sure you check that on your own. I'm not going to do that right here, but if you were to include price, you should find that. And what I'd like to focus our attention on for the moment is including the binary sale, the binary promo variable. as a predictor in the regression. Remember, promo was not a numeric variable in the original data set. And if we look at the promotion column, you see a bunch of zeros and ones as we go down, meaning this is actually a categorical variable that we've coded numerically. And you might say it looks like a discrete numeric variable. You wouldn't be really wrong in making that argument. It can take on 0 and 1. It's a discrete set of values, but it's really a categorical variable. The zeros could have been no's, the ones could have been yes, and we've just coded that numerically here, which I'm going to argue is very convenient in that we can copy that column and include it in our regression just like we did the numeric columns that were ad spend and impressions. Okay, so we're now going to consider here building another multivariate model, not a bivariate one, a multivariate one where we're going to predict sales, but we're going to include all three of these X variables. Okay, we saw that impressions was not significant when we controlled for ad spending on the right as well. Okay, let's see what happens with the promotion. Okay, how does the promotion affect sales? Intuitively, you might think, oh, well, it was positively correlated with sales, right? Promotion and sales were positively correlated. So I might expect promotion to be driving sales. Okay, but we have to be a little careful in making this assertion here because promotion is also positively correlated with both ad spend and impressions, both of which are also included in the model. Okay, so we're going to see that if we control for ad spend and impressions, it may take a lot of the oomph away from the effect promotion actually has on sales. Okay, but let's go ahead and again invoke our regression toolkit using the data analysis toolkit. So I'm going to click on that data analysis button just like we did before. I'll go ahead and select the regression tool, hit OK. Y input range is going to stay the same. For the X input range now, we want to go ahead and just include that promo column as well. And we'll call this one model 3. Model 2 had 2 X variables. Model 3's got 3 X variables. And let's go ahead, we'll zoom in. And we will format. Okay, so here is our most complex model. Most complex in that there are 4 parameters the computer needs to estimate. What are the 4? The computer needs to estimate the intercept, which is our beta 0. It's got to estimate the beta 1 slope coefficient on ad spending, the beta 2 coefficient on impressions, and now it's got to estimate the beta 3 coefficient on promo. Okay. Notice the coefficient on ad spending is still fairly robust to the inclusion of the other variables. In Model 2, the effect that ad spending had on sales was roughly a 19 effect positively. When we increase ad spending on one, it would drive sales up by roughly 19 units. We're getting roughly the same thing here. So it's kind of telling us in Model 1, 2, and 3, the correct thing we did there was to include the ad spending. We're getting that result. That feature is robust in the inclusion of all those models. We can still see the standard error is pretty low in that the t statistic is very large, right? Much larger than 2. The p-value is very small. And the lower and upper bounds in the confidence interval are pretty tight, and they're not changing value from positive to negative. They do not include 0 within that range. Okay. However, when we take a look at the impressions variable, the impression still is statistically insignificant. We have the same issue. The t statistic is very small in magnitude, smaller than 2, right? The p-value is very large, much bigger than 5%, up at 91%. And the confidence interval bounds switch from negative to positive. And all three of those things there, small t-stat, large p-value, and the confidence interval switching from negative to positive, are all indicative of impressions being statistically insignificant. Now, the promo variable here is an interesting one because it can only take on two values. It can only be 0 or 1. So the way we interpret the coefficient is going to be a little trickier. And what does the coefficient generally tell us? Well, that tells us if x goes up by 1, how many units y goes up. And meaning, if x goes up by 1, well, what's promo? It can only be 0 or 1. So that means if we go from 0, no promotion, to 1, running a promotion, sales actually goes down by roughly 865 units. Meaning the model here is predicting that in the presence of ad spending and impressions controlling for those other two variables, it looks like the promotion is actually hurting sales. And again, that might be counterintuitive because we saw in the correlation matrix that promotion was positively correlated with sales. Why is that happening? Well, remember, promotion was also positively correlated with impressions and ad spending. Okay, now the other thing to note here is that the t statistic is very small in magnitude. The p-value is much bigger than 5%. And again, the lower and upper bounds on the confidence intervals go from a negative effect to a positive effect. So as tempting as it is to look at this and say, hey, we should fire the marketing people running the promotions, it's really not a significant feature of model number 3. Neither are impressions. Okay, so for model 2, we had just ad spend and impressions. Impressions was not significant. Model 3, now we have 2 individual variables that are not significant. Okay, what are the 2 variables that are not significant? Well, still impressions was insignificant, but also now the promotion is insignificant. Okay, so if you have a categorical variable and you want to include it in your regression, it is possible to do that if that categorical variable is coded numerically in an interpretable way, like the promotion was coded here. 0 if there's none, 1 if there is 1. And you can even do this if you have a categorical variable with more than 2 categories. I will show you how to do that in a moment here. Okay, but let's go ahead and take stock of a few things in comparison in terms of our model selection. In fact, let me go ahead and make a new tab, and I will call this new tab Model Comparisons. And in this new tab, what I'm going to do here is just grab the output for each model. Got it. There's a model 1 summary. And then over here, we'll put our model 2 summary equals, and then we'll just grab all the summary output from model 2. And then here we'll put all our model 3 summary statistics. If you want to get rid of the zeros, that is appropriate. But here's model 1. That's all, I guess, in one. Careful here. I pasted it all into like one cell, so just an FYI. But we can remember here, insert a row. 1, 2, model 3. And it might make sense. You may recall that if we add variables to a regression, that will only make the R squared go up. So it should make sense that the model with the highest R squared is in fact model 3, 8.5397. Model 2's R squared was 0.5389, and model 1's was the lowest, 0.5386. Meaning model 3 fits the data the best. Okay, but fitting the data is not necessarily the goal. We want to predict well And we may be predicting better with models that are simpler. If you're interested in figuring out how do we know which model predicts the best, take a course on predictive analytics where you learn about training and testing models, the difference between those things. Hey, for now, in terms of thinking about model selection, hey, we do not want to use just the R squared because that's always going to just tell us pick the model with the most variables. Rather, we said the adjusted R squared gives us kind of a better idea by including some penalty, some trade-off for including an excessive amount of variables. And you'll notice that the model with the highest adjusted R squared is actually model number 1, 0.537. It drops a little bit as we go to model 2, 0.5364. And model 3 actually has the lowest adjusted R squared. And you'll also notice model 1 has the lowest residual standard error. So the forecast error of model 1 is lower by 5 units compared to model 2's and by 8 units roughly compared to model 3. So again, if I had to compare these three, which one is predicting better? I might be more inclined for model 1 because it is not as complex as the other two and it didn't include these extra variables that were not as informative. So let's go ahead and wrap up this segment here. We will pick up with one more segment. We'll build one more dummy variable model where we include a categorical variable on the right-hand side. We did that with model 3 by including the promo variable on the right. But the promo variable was convenient because in the original data set, it was already coded for us as a binary 0 or 1 numeric coding. But let's suppose I wanted to try to control for a different categorical variable, the day of the week, maybe. Like, for example, are sales on Saturday different than sales on any other day? Is a Saturday driving sales in a way that's different than other days? There is a way we can actually create our own new numeric variable, a numeric coding of that categorical variable, and we'll wrap up with the next segment in doing that. We'll build a fourth model where we will not include maybe some of the things in models 2 and 3 that we already saw were insignificant, but we will code up a new dummy variable to think about including in model 4, and we will wrap up that segment, the following segment, with a comparison of all 4 models. And that'll be it. So take care. Stay tuned for more.